Welcome back. This is Unit 7.2, Solution Equilibrium. And this reading is on various pages of Book 2 that I sent you. And from Book 2, here are the pages for KEQ, and this is the equilibrium constant we're going to talk about what these mean. It's page 150 to 162. For the solubility product constant, that's page 241 through 250. And for the acid base, 296 through 324. So first also, let's talk about the equilibrium constant KEQ. When a reaction takes place, not all reactions go from the reactants to the products and then stop. Some reactions continue to go toward the right and then back toward the left, and they settle down in what's called an equilibrium. So you can kind of think about this as like a scale where you have a pan on the right and a pan on the left. When you put things on the scale, it's going to go back and forth, up and down, and then eventually it's going to settle out and stop, and that's what equilibrium is called. So pause the video and write these down. All right, so the point in a reaction where the concentrations of the products are no longer increasing or decreasing, and the concentration of the reactants in the reverse reaction are no longer increasing or decreasing. And this is expressed as KEQ, the equilibrium constant. And this is a derived formula for the equilibrium constant in terms of the concentrations of the reactants and the products. And it explains this in the book if you want to look over that, if you're interested in knowing how they derive this. It's not important for you to know that at this level, but it's there if you want to look at it. All right, so here we have an example reaction. This is Cr2O7. It's an ion, -2 charge, plus water, and it's going to 2 hydrogen ions and 2 CrO4 ions at -2. And you can see this arrow here. It's going towards the right and towards the left. That means that it's going to these ions, and these ions are reforming back together to this. So it's going back and forth. And so when we write the KEQ expression, we're going to take the concentrations of our products divided by the concentrations of our reactants. And now we're going to exclude solids and liquids. We do not include those in the KEQ expression. So normally when you see these equations, like in your homework or your problems, it's going to have the state in parentheses right here. So it'll say AQ for aqueous, an S for solid, an L for liquid, or it could have a G down there for a gas. So it will have those. This equation doesn't have it though. Another thing that I want to point out about the KEQ is that your coefficients here, when you write these in concentration, so remember the brackets mean the concentration in molarity, these coefficients become exponents. So this 2 becomes that 2. So that's where we get these 2's. If you have 2 moles of CrO4, it's the concentration double 2 of those. Okay? So make sure that you get that and see that. All right, so here's the sample problem. What is the equilibrium constant for the equation if 1.45 moles of NO2 and 0.1 moles of N2O4 are found at equilibrium in 127 milliliters of a solution at 92 degrees Celsius? And it provides you here with the equation. Okay, and both of these are aqueous. So how will we work this out? Well, we have our equation here, so we're going to write our KEQ expression. So you take the products, concentration of the products, divided by the concentration of the reactants. Now here we have a coefficient of 2. When we balance this out, we get a 2 here. So this 2 becomes the exponent of this molarity. Okay, so we have our KEQ here. All right, so since the brackets here, we're substituting in molarity, we have to look at, we have a 0.1 moles of N2O4 in 127 milliliters. So we have to calculate the molarity. So remember from our last section, molarity or concentration is equal to moles over volume. So we're going to take our moles, which is 0.10, divided by our volume in liters. So this is 0.127 liters. We're going to divide that out, and that's how we get the 0.79. Then we're going to do the same thing with the NO2, 1.45 divided by 0.127, and that's how we get the 11.42. Okay, now this is to the power of 2 because of our coefficient here. So when we do this math, we come out with a KEQ of 6.06 times 10 to the negative 3. Okay, so that's the equilibrium constant for this reaction at this temperature. Okay, and this number is a unitless number. It does not have any units. Okay, because this is a molarity. This is a molarity. When we divide those cancel out. All right. All right, so here we have another problem. It says a student placed 7 moles of NH3 in a 0.5 liter flask. At equilibrium, 6.2 moles of N2 was found in the flask. What is the equilibrium constant? All right, and so here we have our equation, and this is called a Haber process to create ammonia. And you'll see this word in your reading. So just know if you see Haber process or this is what it is. So when we balance the equation, we get 2 NH3 goes to N2 plus 3 H2s. All right. And so to help us do these problems, we draw what's called an ice chart or an ice box. And some people say rice chart. They put an R here because this is the reaction. You put the reaction in this top box. But I just say an ice chart or an ice box. Okay. All right. So you write your reaction here. And then for each one of these, you're going to put in a separate column. So we take our reactant and it has a column. We take our first product, it has a column, and then our second product has a column. Now, what you want to do when you do this is you want to fill in this information. So it says here that a student placed 7 moles of NH3 in a 0.5 liter flask. So this is what we're starting with. So ICE, this means initial concentrations, the change in concentration, and then E is equilibrium. So it tells us here that we're starting off with 7 moles of NH3 in a half liter flask. So we know to get molarities, now these all have to be in molarities, that we're going to take this 7.00 moles and we're going to divide it by liters to get molarity. So that's how we get the 14.0 molars. Now at the initial concentrations at the beginning, all of this is your NH3. So we have none of this yet and none of this because this reaction hasn't happened yet. It's the initial concentrations. Then the second part of the question, it says at equilibrium, 6.2 molar N2 was found. So at equilibrium, that's the E, N2 6.2 molarity was found. Okay, what is the equilibrium constant? All right, so over here to this side, I have all of the information that we're going to put here, and here, all of the information that we're going to put in our box. So let's get our equilibrium expression first. So it's going to be our products, the concentration of our products. So N2 is going to go on top here. There's no coefficient there, so we don't need to put in an, oops, I'm looking at the wrong, here, this equation. There's no coefficient, so I don't have to put in an exponent. And then H2 is going to be up here too. It's a product. We do have a coefficient here, so we need a 3 here for the exponent. So we're going to drag this 3 here. And that's going to be divided by the reactants. So we have NH3, concentration of, and it's to the power of 2. So I'm going to put a 2 here. So this is our KEQ expression. Now, in order to solve this, we need to plug in numbers here. Well, here's where the chart comes in. We have to look at this and we have to decide if this is what we start with and we ended with this much, the change here has to happen. So if we ended with this much, if we started with 0 and we end with 6.2, what's the change? Well, it's going up by 6.2. So I can put this in here. So this is going up by 6.2 because if it started with 0 and ended here, that's the change. Now let's look at this. We have 1 mole of this to 3 moles of this. So if 1 mole goes up by 6.2, 3 moles is going to go up by, multiply this number by 3, you're going to get 18.6. So this went up by 18.6 concentration. So if we started with 0 and it went up by 18.6, then the change, the equilibrium, is going to be 18.6. All right? Now for this. This is 2 moles. So if we know this 1 mole is 6.2, 2 moles is going to be 12.4. Now, this is going down because this is now turning into this. So the NH3 is turning into N2 and 3 H2s. So this, while these are going up now, this is going to go down. So this is going to be a minus 12.4 because it's twice this. So 14 minus 12.4 is going to leave us 1.6. So now we have our ice chart filled out and we didn't use this column. Sometimes we have more than 2 reactants or more than 2 reactants or more than 2 products. So that's why I have this extra box here. But we didn't use it, so don't worry about it. All right, so now we can fill in our concentrations. So at equilibrium, so we're looking at this bottom one right here. At equilibrium, the N2 was 6.2. So I'm going to take my 6.2 and that goes here. At equilibrium, the hydrogen was 18.6 and it's to the 3rd power. So we have 18.6 to the 3rd power here. And our NH3 right here is 1.6 to the 2nd power. So I'm going to take 1.6 to the 2nd power and put it here. Now it's just a math problem. So if we take and we do this math problem, we're going to come up with a KEQ of 1.6 times 10 to the 4. Okay. All right, so that is the KEQ, equilibrium constant for these concentrations in this flask. All right, and so you're going to have a different ice chart for each one. And this is, we only do ice charts for weak acids. And we'll see this, an example of this, weak acids, weak bases, and insoluble salts. Okay, and we're going to see an example of that, like I said. All right, and here's another one. Okay, so see if you can work this out. The answer is 0.13. So pause the video and see if you can look back to this example and work this one out, and then I'll work it out for you. Okay, so a sample of 6 grams of carbon was placed in a 1 liter flask containing 1.4 moles of oxygen. When equilibrium was established, 1.2 grams of carbon remained. Determine the KEQ. All right, so let's go ahead and write our KEQ expression. This is going to be our products over our reactants. Okay, so we have the concentration of CO, and it's a coefficient of 2, so I need to put a 2 here, exponent, over the concentration of our reactants. Now remember, we do not include solids or liquids, so we're not going to include this solid. So it's just going to be over this one. So this is over oxygen, okay? And we don't have, oh, did we forget to balance this? We did. So let's go back and balance this. Let me erase this. So we have 2 carbons here. So I need 2 carbons here. We have 2 oxygens here, and we have 2 oxygens here. So it doesn't change anything. It does not change this expression because we didn't have to add an exponent here. I'm sorry, a coefficient here. So no exponent here. So here we have our KEQ expression. Okay, so now we need to do our ice chart. Okay, and so for this top part, I'm going to, pardon the crooked lines, 2C. I'm going to do ICE here. All right, so 2C plus O2 yields 2CO. All right, so we don't include this because remember it's a solid, so that's going to be X'd. So all we're interested in is this part. Now we're going to have to do some calculations here, maybe to find out some of these. All right, so it says a sample of 6 grams of carbon were placed in a 1.0 liter flask containing 1.4 moles of oxygen. So that's going to be important, 1.4 moles of oxygen. And the size of this flask is 1 liter. So it's being placed in this much oxygen. So this is the initial concentration of oxygen. So 1.4 moles in 1 liter is just going to be 1.4 molarity. And so that's how much oxygen we're starting off with. So I can go ahead and put that. This is kind of like listing, when we do glues, listing your givens. When equilibrium was established, 1.2 grams of carbon remained. All right, so we started off with 6 grams of carbon and 1.2 grams of carbon remained. So we need to find out how many moles was used here. So if I take 6 and subtract 1.2, I'm going to find that the number of moles used of the carbon was 4.8 grams. So we used 4.8 grams. How many moles is that? Well, here's where we have to do a conversion, and this is of carbon. So we want to get rid of grams of carbon, convert it to moles of carbon. 1 mole of carbon is 12.01. Okay, cancel what you can cancel, so that's going to leave us moles of carbon. So 4.8 divided by 12.01 is going to be 0.3997. 0.3997 moles of carbon used. So this is going to tell us that since this is a 2 to 1 to 2, if we used here 0.3997 moles of carbon, we're only going to use half as many moles of oxygen because it's a 2 to 1. So we're going to take this and divide by 2, and that's going to let us know how many moles of oxygen we used. So we used 0.1998 of oxygen. Okay, now this is still in a 1 liter flask. So if I use this many moles of oxygen, that means that the concentration, since it's in a 1 liter flask, the concentration of the oxygen that I used was 0.1998. So this went down by 0.1998. So if we take our 1.4 minus 0.1998, that's going to give us 1.2 that we have left over at equilibrium. Okay, and this is 0, so we use 0 of this. So if this went down by 0.1998, this is double this. So we're going to go back to we use twice as much. So 0.1998 times 2 is 0.3996. And that went up by that much. So if this goes down, this goes up. So if we started at 0 and we went up by this much, then we're going to end with 0.3996. All right, so now we have all the numbers that we need to plug into this equation. So KEQ is equal to carbon monoxide concentration. Remember, this is at equilibrium. So we have 0.3996. Okay, and this is squared over the O2 concentration, 1.2. Okay, so now this is a math problem. Okay, so 0.3996, and that's going to be squared over 1.2. We're going to get 1.3 times 10 to the negative 1. 1.3 times 10 to the negative 1. And this matches our answer because this is not in scientific notation where this is. So if we just convert this over to regular, then negative 1 means your decimal point's going to go this way. So we get 0.13. All right. And that matches what we should have got. All right, so let's talk about the solubility constant product now, the KSP. We've been talking about KEQ, equilibrium constant. So really KSP is the same principle. So it says here, the same principle applies to the solubility of compounds in water. KSP is called the solubility product constant. The ions separate, and that's in equilibrium with the recrystallization. However, since the reactant side right here is a solid, it's omitted from the KSP expression. Because remember, we don't include solids or liquids. So if we remember that, it's just the expression, remember, is products, a concentration of the products over the concentration of the reactants. But if the reactants is a solid and we don't include that, then all we have left is the concentration of the products multiplied together. So we're going to take this concentration multiplied by this concentration, and that's going to be our KSP. So PB2 right here, and then we have 2Cl, so we have Cl to the power of 2. Okay, so remember, when we do these coefficients as exponents. So this is the KSP expression for this reaction. All right. So when we're working out problems, one thing that we have to have is called the KSP. So sometimes when it depends on the problem, you may have to look up or you may have to be given the KSP if you're trying to find concentrations. So for this particular problem, we're calculating the KSP, all right? And we should get 7.1 times 10 to the negative 5th here. So if we take CaSO4 and we look on our solubility chart, we're going to see that this is an insoluble salt. It's insoluble. Now, if you remember back to our last section, I explained that insoluble salts, really every salt is soluble to some extent, but it's only labeled as soluble at a certain point when you have a certain amount that will dissociate in water. But everything is soluble to a point. So this is considered an insoluble salt. So the separation of the ions is going to be, the concentrations are going to be very, very low. See here we have 7.1 times 10 to the negative 5. That's a very, very small number. All right, so CaSO4, if it does separate at a small amount, it's going to separate into calcium ions plus sulfate ions. Okay, and so the molarity is 8.4 times 10 to the negative 3 at a particular temperature. All right, so we're going to need to balance this reaction. And since we have, this is a +2 and a -2, we don't have any coefficients here that we're going to add. So this is a 1-to-1 ratio here. So we don't have to have any coefficients here for these two ions. So if this is a 1-to-1-to-1, if we have 8.4 times 10 to the negative 3 molarity, it says that the molar solubility, so that's what it means. Since this is 1-to-1-to-1, then this is going to be 8.4 times 10 to the negative 3. And this is 8.4 times 10 to the negative 3. So if our KEQ expression is the concentration of calcium times the concentration of, oops, not 8. I was thinking SO at the same time. SO4, that's a -2. Then we're going to substitute in these numbers here. So 8.4 times 10 to the negative 3 times 8.4 times 10 to the negative 3. Okay, so when we multiply those together, we're going to get 7.056 times 10 to the negative 5, or 7.1 times 10 to the negative 5th. Okay, and that matches what we should have got for our answer. All right. So what types of problems are we going to use this for? Well, if it says find the concentrations of each species, and remember when it talks about species, it's just talking about what ion. Okay, it could be a hydrogen ion, it could be a hydroxide ion, it could be a calcium ion. Okay, so that's what it means when it talks about species. It talks about either ions or compounds. Find the pH or pOH of the solution. We're going to talk about those in just a moment. Find the percent dissociation of the substance in solution, and this is for weak acids and weak bases. And it says find the solubility of salt. Okay, remember all salts are any positive cation and negative anion. Well, here it said percent dissociation, so I've given you the calculation for percent dissociation. So it's the amount dissociated over the initial amount times 100. So we're going to be using that in just a moment. All right, so pause the video and write down the problem solving steps here. These steps will help you in solving these problems. All right, so identify the type of substance that it is. So is it a weak acid? Is it a weak base? Is it a strong acid? Is it a strong base? Is it a soluble salt? Is it an insoluble salt? Because that is going to dictate whether we draw a nice chart or not. If it's a weak acid, a weak base, or an insoluble salt, you're going to have the Ka, Kb, or Ksp values. And those are charts that I've given to you. So you have to look that up, or it could be given to you in the problem. You're going to either solve for X or S. For soluble salts, a lot of books and instructors use S for that variable there. And for weak acids and weak bases, an X. I just tend to use an X for everything. I solve for X because in my TI Inspire calculator, I use X as a variable when I input equations. And then you're going to calculate the desired quantities. So if you have an ice chart, then that's where you're going to calculate the quantities to fill up the ice chart. All right, so here we have the general equations for the dissociation of a weak acid and a weak base. Here we have HNO2. It's going to dissociate into hydrogen ions and nitrite ions. This is nitrous acid, so this is a weak acid. Remember, HNO2 is nitrite, HNO3 is nitrate. That would make nitrate a strong acid, but this is nitrous acid. So it's a weak acid, so that's how that dissociates. And also the dissociation of a weak base. BaOH2 dissociates into Be plus 2 and 2 OHs. All right, so for a 0.1 molar solution of HC2H3O2, and this is acetic acid, this is the acetate ion with hydrogen. Find all the species concentrations at equilibrium and the percent dissociation. So it gives us the Ka here for that. But if we didn't have that, then we could look it up on one of those charts that I gave you, the Ka chart. All right, so the first thing we need to do is we need to have identify what type of substance this is and have our reaction. So this is a weak acid. So we have HC2H3O2 is going to dissociate, double-ended arrow just to make it official, hydrogen ions plus the acetate ion. Okay, and balancing this equation, we see that it's already balanced, so it dissociates 1 to 1. So I'm going to write HC2H3O2, this is where I put my reaction, okay, to H hydrogen ions plus C2H3O2 ions. We're not going to use this box here. There's nothing there for it. Find all the species at equilibrium and the percent dissociation. So we have the Ka here, 1.8 times 10 to the negative 5. All right, so this tells us we have a 0.1 molar solution of this. So 0.1 molar solution of this. Now, this is a weak acid, so this is going to go down by 0.1 minus X by some number. We don't know that yet. This is going to start off at 0, and this is going to start off at 0. All right, so if this is, since it's 1 to 1 to 1, if this goes down by X, this one has to go up by X, and this one also has to go up by X because it's 1 to 1. All right, so here's a little piece of information that I need to tell you. Because this is a weak acid, its dissociation is going to be so small. So the amount that it dissociates is going to be so small that this X is not going to affect the significant digits of 0.1. Now let me explain that. So let's just say the dissociation of this was 1.0 times 10 to the, and since it's a very small dissociation, let's say 0 to a negative 5. Well, if we were going to turn this into a standard notation, we would have to move the decimal over 5 times to the left. 1, 2, 3, 4, 5. So we would get 0.00001. So if we took 0.1 minus 0.00001. This number is so much smaller than this number that it's not going to affect the significant digits. So in order to make this math easier, what we say to do is, when we're calculating x, is to ignore this x here. So this is going to be 0.1. This is going to be x, and this is going to be x. So now for our dissociation equation, we have, and we're calculating KSP is equal to, well, actually Ka, because this is an acid. Ka is acid, Kb is base. So this is reactants over products, and this is a liquid, so we're not going to include this part. So it's this times this. So we have the hydrogen ion times the acetate ion. Okay, so our Ka is 1.8 times 10 to the negative fifth is equal to, and then we're going to substitute in here x and x. All right, so 1.8 times 10 to the negative fifth is equal to x times x. X times x is x squared. Okay, so if we're going to solve for x, we're going to take the square root of both sides. So the square root of 1.8 times 10 to the negative fifth is equal to x. All right, so now that's a math problem. We can solve for x. So if I'm taking the square root of 1.8 times 10 to the negative fifth, I'm going to get 4.24 times 10 to the negative 3. So x is equal to 4.24 times 10 to the negative 3. All right, so now we can solve for this. So I'm going to remove this. And I can go ahead and put in, I'm going to go ahead and put in these numbers here. So x was 4.24 times 10 to the negative 3. We're going to go ahead and solve 0.1 minus 4.24 times 10 to the negative 3. Okay. We're going to get 9.58 times 10 to the negative 2. All right. Okay. So it says find the concentrations of all the species at equilibrium and the percent dissociation. So what we're going to write is, and I'll write it right here, the concentration of our hydrogen at equilibrium is 4.24 times 10 to the negative 3. Our C2H3O2 is 4.24 times 10 to the negative 3. Our acetic acid is 9.58 times 10 to the negative 2, and these are all molarities. All right, so that's each species and the percent dissociation. All right, so remember the percent dissociation is the dissociated amount divided by the initial amount. Okay, let's go back to that and look at that. The amount dissociated over the initial amount times 100. So we're going to have 4.24 times 10 to the negative 3 over the initial amount, 0.1. Then we're going to multiply this by 100. Okay, and we're going to get our percent dissociation. So 4.24 times 10 to the negative 3 divided by 0.1 times 100. Okay, and we're going to get 4.24%. All right, so mixing strong acids and strong bases. So when you mix strong acids and strong bases, it's called a neutralization reaction. It's a special type of double replacement reaction because the acid neutralizes the base, producing a salt and water. So if you had sulfuric acid here plus calcium hydroxide, okay, so this is going to rearrange. This H is going to go with this OH, right? And this CA is going to go with the SO4. So inside, outside, we're going to have water and calcium sulfate. And calcium sulfate is an ionic salt. All right, and so same thing here. If we have sulfuric acid and NaOH, it's going to inside, outside, HOH plus one of these, since this is what's called a diprotic acid, one of these hydrogens is going to stay with the sulfate ion. So we're going to have NaHSO4, which is sodium bisulfate or sodium hydrogen sulfate. This is a polyatomic ion right here, the bisulfate ion. So it produces this sodium salt and water, HOH. And I just wrote water, HOH, instead of H2O here. All right, so this is a neutralization reaction. And we do have problems where we combine acids and bases and we figure out, different concentrations. So here's an example. Under controlled supervised conditions, a student adds 35 milliliters of a 0.010 molar hydrochloric acid solution with 15 milliliters of a 0.01 molar sodium hydroxide solution. So he's mixing an acid and a base here. Find the concentration of either the hydrogen ion or the hydroxide ion, which one is left over here, because this is not in equal amounts or equal concentrations. Well, it's in equal concentrations, 0.01, but it's not in equal amounts. So he's adding more, 35 milliliters, he's adding more of the acid to 15 milliliters of the base. So we need to find out the concentration of either the hydrogen or hydroxide that's left over. Okay, so we're pouring one liquid into another liquid. Okay, so from the last section, do you know what we call that? Do you remember what we call that when you're pouring one liquid into another liquid? Okay, it's called a dilution. So we know that for a dilution, M1V1 is equal to M2V2. We have to figure out, because we're diluting these ions, so it's a 0.01 molar at this much, 35 milliliters, but we're combining this with 15 milliliters. So we're increasing the volume. So we need to find out what molarity it's going to be at that volume. So we have to do a dilution problem first. So our M1, and let's just work with the hydrochloric acid first. Okay. Our M1 is going to be 0.01 molar. Our V1 is going to be 35 milliliters, but we need liters, so 0.035 liters. Okay, we're going to look for our molarity too. We don't know what concentration this is when we mix these two together, So that's what we're trying to find. But our V2, so we're mixing 35 milliliters with 15 milliliters. So 35 plus 15 is going to be 50. So our V2 is going to be 0.05 liters because it was 50 milliliters. All right, so we're solving for M2. M2 is M1 V1 over V2. So now let's substitute these in. So grab your calculators. 0.01 is M1 times V1, 0.035 over 0.05. So that new molarity is 7 times 10 to the negative 3. Okay, so that's the molarity of the hydrochloric acid. Now let's do the new molarity of the NaOH. All right, so we have M1, the beginning molarity is 0.01. The beginning volume is 15 milliliters, so it's a 0.015 liters. We're going to be calculating the second molarity, the diluted molarity, and our second volume is going to be the same as the second volume here, 0.05 liters. All right, so again, M2 is equal to M1 V1 over V2. So M1 is going to be 0.01 times V1, 0.015 over 0.05. This is going to give us 3 times 10 to the negative 3 molarity. Okay, so how many moles of hydrogen do we have? So now we're looking at molarity because remember, 1 mole of acid, strong acid, will neutralize 1 mole of a strong base. So moles is equal to molarity times volume. So we're looking for moles. How many moles? So we're going to take our molarity times our volume. So here's our molarity times our volume, which is 0.05 liters. And that's going to tell us how many moles of acid that we have here. So again, picking up your calculator, 7.0 times 10 to the negative 3 times 0.05. It's going to give us 3.5 times 10 to the negative 4 moles of our acid. Okay, same thing here. 3.0 times 10 to the negative 3 times 0.05. That's going to give us 1.5 times 10 to the negative 4 moles of our base, hydroxide. So what are we going to have left over? Well, 3.5 times 10 to the negative 4 and 1.5 times 10 to the negative 4. We've got more acid than we do base. So this much of the base is going to neutralize this much of the acid. So we're going to subtract these two. And that's going to be how much hydroxide we have left over. So 3.5 times 10 to the negative 4th minus 1.5 times 10 to the negative 4th. That's going to be 2.0 times 10 to the negative 4 moles of hydrogen left over. Now I said that's going to give us our concentration of the hydroxide. I was mistaken on that. It's going to not give us a concentration. It's going to give us how many moles. And since the hydrogen was the one that was in excess, we had more of it, it's actually going to lead us to getting this. But we're not finished yet because this is just moles. So we need to get a molarity. So it's moles divided by liters. So now we need to convert this back into a molarity. So we're going to take our answer and put it over 0.05 liters because that's how much volume we have. So divided by 0.05. Okay, and that's going to give us 4.0 times 10 to the negative 3 is the concentration now of the hydrogen ion that we had left over. So you just have to, look at this, remember everything that we've done before, and you have an example problem like this in your problems that you're working out. So you'll get an opportunity to work on one of these on your own. All right, and so finally, coming to the pH scale. Now you've heard about the pH scale, and this is how we measure the strength of an acid or the strength of a base. This was devised by Danish chemist S.P. Sorensen. He described the pH as the power of hydrogen. So that's where they get pH. Power of the hydrogen ion, pH, thus giving it the abbreviation pH. It is actually calculated as the negative logarithm of the concentration of hydrogen ions in a solution. So I know maybe algebra 2, maybe you've started talking about logarithms. We're going to use the base 10 log. So in this last section, we calculated the concentration of hydrogen ions in a solution. Here, the concentration of hydrogen ions in solution. Okay, and so now we can assign a more meaningful number to that to describe it on a scale from 0 to 14. It's actually, I put here 1 to 14, but it's actually 0 to 14 because you can have an acid that's a very, very strong acid that's just a little bit less than 1. Okay, for the power of the hydrogen. So the pH, as I said here, is the negative log of the concentration of the hydrogen ion. And this is the only formula that's provided for you in the reference materials. And I know you get to use those reference materials. So in order to get all of the other ones, you either have to know how to rearrange logarithms or you just have to memorize. Okay, so if we have the pH as a negative log of the hydrogen ion concentration, then the pOH is the negative log of the hydroxide ion concentration. And this, remember, OHs are for bases. If we rearrange this first one, pH, for solving for the concentration of the hydrogen ion, we get that it's equal to 10, since this is base 10 logarithm, 10 to the negative pH will give you the concentration of hydrogen ion. And conversely, the concentration of hydroxide ion is 10 to the negative pOH. All right, so on the pH scale, an acid is anything that's less than 7. So 7 less than 7. So it's 0 to 7 is for an acid. And for a base, it's anything greater than 7, so 7 to 14. If it's exactly 7, that's called pH neutral. Okay, 7 is neutral on the pH scale. So anything under 7 is an acid, anything over 7 is a base. All right, and so we were talking about KEQs at the beginning of this. KEQ for water is a special equilibrium constant. It's KW, W for water. And that's where you have the hydrogen ion multiplied by the hydroxide ion. This product of these two multiplied together is always going to give you this number, or a number very, very close to that because of rounding errors. 1.0 times 10 to the negative 14. That's the KEQ or KSP, or equilibrium constant for water, KW, 1.0 times 10 to the negative 14th. Okay, so if we look at this and we relate this back to our pHs, then we get another equation, which is pH plus POH is always going to be equal to the number 14. And that's going to be very important when we start working out these pHs in these tables. All right, so under controlled supervised conditions, this is the last problem that we're looking at. A student adds 35 milliliters of this acid to the solution of 15 milliliters of this. So remember this question right here that we just worked out. Okay, so find the pH, POH, the hydrogen ion concentration, and the hydroxide ion concentration. So if we look back, we did find the hydrogen ion concentration here. So we found that the concentration of the hydrogen is this. So I'm going to transfer this number over to, instead of working it all out again, I mean, what would be the point? Okay, so we're going to transfer, this is just moles of hydrogen. Here is the number we want. 4.0 times 10 to the negative 3. We're going to transfer this molarity over to our other problem. Okay, so 4.0 times 10 to the negative 3 is the concentration of the hydrogen ion that was left over. All right, so from this, we're going to calculate pH, POH, and OH. So let's look. If we have the hydrogen ion concentration, we can calculate the pH, because if you look at your formulas, pH is equal to the negative log of the hydrogen ion concentration. We calculated that as 4.0 times 10 to the negative 3. So to get the pH here, this is equal to the negative log of 4.0 times 10 to the negative 3. Now remember, these brackets mean molarity. It's the same thing. Right? So now we're going to put that into our calculator. So let me fire up this calculator here because I want to show you exactly how I'm entering that in. And this is the TI Inspire software that I sent you way at the beginning, right after spring break, because Texas Instruments has most kindly allowed us a 6-month license to this. So you can download this software. Just go back to that announcement and you can download the software and you can use this on your computer, or you can just use your calculator. It doesn't matter. All right, so we're going to take the negative log of 4.0 times 10 to the negative 3. Okay, so the way we do that is negative, here's the negative sign here. Now we want to hit the log button. And on the TI Inspire, the log button is the second function right here. So we need to do control this button and get the negative log. Now, I said this is base 10, so logarithms for pH are always base 10. So here it's asking for base 10. That's what that is. Now, on your other TI calculators or other calculators, you do not have to put that 10 in. There's not going to be a place for that. It's just going to assume it's base 10. So you don't have to put that in. But on the TI Inspire, you do have to put in that it's base 10. So here's where you put in that concentration. So that concentration was 4.0 times 10 to the, and that's the EE button. You have to use the EE button here, negative 3. So 4.0 times 10 to the negative 3. Okay, so that's what you put in here. And then you hit enter, and it's going to give you this number. Now, here's a tip. When you're calculating pH and POH, it is always, without exception, always going to be a number between 0 and 14. If you get anything else over here that is not a number between 0 and 14, you have done something incorrect. So here we get 2.4. Let's just round it to one decimal place, 2.4. Okay, so going back to here, we just calculated the pH of this is 2.4. All right, so when you're deciding whether this is an acid or a base or neutral, you always look at the pH, this value here, pH. So remember, 0 to 7 is acid, 7 straight up is neutral, and 7 to 14 is a base. So this is 2.4, so this is going to be acid. So we had more acid than we had 15 milliliters of sodium hydroxide, which is the base. So it makes sense that since we had more acid left over, that this pH would be 2.4 and this would be in an acid. This would end up being an acidic solution. All right, but we still need to calculate the others, this. All right, so if we have our pH is 2.4, our pOH is, remember, pH plus pOH is equal to 14. So if we have pH, then we just take 14 minus 2.4, and that's going to give us our pOH. Okay, so 14 minus 2.4 is going to give us 11.6 for our pOH. And these don't have units on it, 11.6. All right, so we have our hydrogen ion concentration, we have our pH, we have our pOH, we just need to calculate the OH concentration. Now, these are all done in water, all of these reactions. So in water, you're always, even if it's an acid of 2.4, you're always going to have a concentration of OH because it's in water. And remember, in water, hydrogen separates from OH. Okay, these are in equilibrium. You have hydrogen ions and OH ions. So we need to calculate what that is. So if we want to know the hydroxide ion concentration, okay, we're going to take the pOH, 11.6. It's going to be 10 to the negative pOH, so 10 to the negative 11.6. And that's going to be the concentration of OH that we have in there because of the dissociation of water. So 10 to the negative 11.6. And this is going to be 2.5 times 10 to the negative 12. Okay. All right. Now, one more check here. I'm just going to show you. You can take your concentration of your hydrogen multiplied by the concentration of your hydroxide, and you're always going to get something that's very, very close, if not exact, to 1.0 times 10 to the negative 14, give or take. So let's try that. 4.0 times 10 to the negative third times 2.5 times 10 to the negative 12, and we get exactly 1.0 times 10 to the negative 14. All right, so this is how you calculate pH, pOH, hydrogen ions, and hydroxide ions. And on your homework, your problems that you're working out, you have a big long chart for you to use these formulas over and over and over and get used to using those. All right, so that is it for this lesson. I know it was long, so I'm giving you extra time to work on this. So make sure that you slap that like button right across the face. Give me a thumbs up, hit the notification bell, and you can be notified of when I put in new videos.